Go Language Programming, Chapter 7, Unit 1. In this unit, we will cover concurrency versus parallelism and POSIX Threads libraries. A system is said to be concurrent if it can support two or more actions in progress at the same time. A system is said to be parallel if it can support two or more actions executing simultaneously. So the concurrency and parallelism are conceptually overlapped to some degree, but in progress clearly makes them different. Basically, in progress meaning that something is happening right now, then versus something might be happening in one after the other one, so one thing will finish which is in the progress, and then the other thing will happen. Okay, so that's what basically in progress makes a difference, meaning it is happening all at one time right now. So concurrency is about dealing with lots of things at once, and basically parallelism is about doing lots of things at once all together. So basically that's the major difference between a concurrency and parallelism. So coming to understand here, if we have a multiple tasks that are executing at the same time but not necessarily simultaneously, okay, so those tasks would be considered as concurrent. Since they are not happening simultaneously, they cannot be considered as a parallel. Concurrency means that application is making progress on more than one task at the same time. Okay, so basically that doesn't mean that all those tasks are happening simultaneously. It does mean that they are happening in the same time but not simultaneously. So that's why it is considered as the concurrence. So those tasks are going through the concurrency. So a single CPU system can not progress more than one task at the same time, but application can progress or application can process more tasks by using thread libraries. So if you have a thread library, that means, or if you are using a thread library in your application, then more tasks can be processed. Okay, but on the single CPU system, still they would not be really considered as that they are happening in parallel. They would be considered they are providing the concurrency. Parallelism means that the application splits its task into smaller tasks. Okay, so once the application will split the task into smaller tasks, that means all those smaller tasks can be running simultaneously. Okay, provided that they are not running on the single CPU system. So for anything that need to be in a to be running as a parallel, it better be on a multiple CPUs. Okay, so each task can be processed in parallel only if there is a multiple CPUs are available. Okay, and they will be happening all simultaneously, all in exact same time. So parallelism requires the hardware with multiple processing units. So basically, that means you need to have some sort of a multiple cores or multiple CPUs to achieve the parallelism. Parallelism cannot be achieved in a single CPU system. So in a single CPU, you may get a concurrency but not parallelism. Okay, so in a single CPU, it is possible to get a concurrency because the scheduler will schedule each task in such a way that um, that that it would seem like they all are running at the same time. Okay, that's because scheduler will be switching or giving a time slice of the CPU to each task, and therefore to us it would look like all those tasks are running simultaneously, even though it is a single core CPU. So now let's look at what are the threads, okay, and what does the thread library gives us. So the POSIX threads, POSIX basically portable operating system interface. The POSIX threads library are standard based thread API for C++. So the newest POSIX thread library is called NPTL. NPTL. Okay, and N stands for Native POSIX Thread Library. So basically, every program that is written in C++ has at least one user space thread. So when we write a program that has main, it starts with the main entry point function. Okay, that main entry point function is already running one thread without even using the any library, any POSIX thread library or any thread libraries. So that would be considered as a single threaded application. So a thread basically is just a sequence of instructions that can be executed independently by a processor. Okay, that's what the thread is. So when we use a thread library, then every thread, the thread libraries are used in your application, which is running in your user space, and then from user space, those threads, they enter the kernel space, and when they enter the kernel space, each user space thread becomes a kernel thread. So in that regard, there is a one-to-one ratio between a user space thread and then the kernel space. So POSIX Thread library allows a program to control multiple different flows of work that overlap in time. So that means that you can have more than one thread that will be running independently in your application, and each thread would be have its own control flow, and they may be uh, going, since they are running independently of each other, they could be one thread might be finishing earlier than the other thread. So the concept about thread is that you have, this is a some program, some application, okay, and within this application there are multiple threads running. These are the threads running, okay, and these all threads would be running within this application's address space. So this is the application's address space right here within this circle. So basically, these each threads are running independently. They don't depend upon each other. So in this case, some thread might finish their work before, so let's say there is a thread A right here, B, and C. So A thread A might still be running, but thread C would finish its work. Okay. And if they are running on a multiple CPUs or multi-core, then it is possible also that each thread would be running on its own core. So definitely the if your system has multiple processor, then the multi-thread application basically will have much more um, uh, easy to finish the task, because because of the threads running independently on each different processor, and um, your application would finish um, its work in much less time. Now, the threads definitely, multiple threads definitely provides a good performance on the multiprocessor. But even if you have a single processor and you're running multi-threaded application on a single or uniprocessor, the your application still would have a better performance, because internally, the scheduler will basically do the for all these threads, the small amount of time will be allocated for each thread to utilize the CPU. Okay? And in that case, we since it would be on the uniprocessor, we would not say that your application is running parallel. It would be considered as it is providing a concurrency. So threads require less overhead than forking or spanning a new process. Okay. Forking meaning that your process is going to create a child process. So whenever there is a child process involved, then there is a parent-child relationship, and that requires more effort to create a child process, and requires more um, more memory will be allocated. Um, if you know if you have a thread, if you create more threads instead of forking the new process, that will require much less overhead. POSIX Thread library under Linux is supported by system calls. Okay, so the system calls are basically supported by the POSIX Thread library. POSIX Thread library provides a lots of different system calls, like for example, mutex locks. If you want to lock some resource, you have a system call for it, which is a part of the POSIX Thread library. Other one is uh, pthread create, for example. That's a to create a new thread. That's a system call. Pthread wait. That's a system call. So all those system calls are provided within the POSIX Thread library. When user space thread enters the kernel space, it becomes the kernel thread. So basically, when you have these threads that we are talking about right here, they are running within this application. Okay, and eventually they will have to enter. So this is a user space right here, and here is a kernel space. And when these threads enter the kernel space, as we talked earlier, it will have 1-to-1 ratio. Okay, so one user space thread will become a one kernel space. So in this case, for this application, it has 3 threads. So when it enters into the kernel space, there will be a 3 kernel threads will be created. Okay, so under Linux, there is a struct called task underscore struct. Task underscore. So this is the struct that is used for application as well, and it is the same struct which is also used for the threads as well. Now, for this struct has fields such as process ID, the status of the process, the memory that is allocated for the process, and many other fields in there. So it's a pretty good size, big struct. Okay, so if it is populated, fully populated, then that means it is for the application, meaning that it is for the some process. But For the threads, this same struct doesn't get populated fully. It is only partially populated, and that's why threads becomes a lightweight. Okay, they are considered as a lightweight processes. So that's how things happen under Linux. Okay, so under Linux there is a data structure called task underscore struct that is used for both purpose. For the application, once it starts running, that becomes a process, and also threads which are running in the application's address space in here, for example, then they are basically using the same struct but not fully populated. So that that is all about the thread library. Okay, so let's look at the Goroutines now. How Goroutines are used and the purpose of the Goroutines. So in Go language, basically, um, you know, we have um, we have the Goroutines. So Goroutines and concurrency are built into the core design of a Go language. Um, they are similar. They are similar to threads, but work differently. So Goroutines are quite a bit similar to thread, but they are not really the same. They are in other languages. The Goroutines are considered like a green threads. Okay, that's the other word that people use, a green thread. And the reason that they use a green thread is because they are very lightweight. Just now when I was explaining about the difference between creating the threads with the thread library, and the difference between a process. Uh, so the process is, which are your applications, uh, they are a little bit heavier, because under Linux, we were just discussing about the task underscore struct, and that get fully populated, and the threads are using the same struct but not populating the whole thing. For the Goroutines, they are even much smaller than the operating system or OS threads, and that's why they are more lightweight. Okay, so Go language also gives you a full support to share memory in your Go routine. So basically, if you have a Go routine, you can share the memory. If you create some memory within the Go routine, you can share that memory. So Go routines usually uses about 2 kilobytes of stack space. Okay, comparing to using OS threads, which is in between 1 megabyte and 2 megabytes of stack space or stack memory. Okay, so that's the one big difference for using a Go routine instead of OS threads. So basically, with the Go routines, it's not hard to run thousands of Go routines on a single computer. Just because it doesn't uses a very big stack space like a OS thread would use. So a Go routine is more lightweight, more efficient, and more convenient than the OS threads. Okay, because because of the way they are designed, and they are managed by not by OS. Okay, so OS operating system doesn't manage the Go routines. Go routines are managed by the application that you write internally, and we will go into more detail very soon. So Go routine run on the thread manager at runtime. So basically, when you write an Go application, every Go application has a runtime system, and runtime system is the one which has a scheduler built in. So every Go application has its own scheduler, and that scheduler is the one which is responsible for managing the Go routines. So we use the to start a Go routine, you can use a Go keyword. So, and then your function name. So basically, that's how you will get the Go routine, or basically that's how you will make the Go routine execute. So that means you can execute any function that that you have written in your in your Go application. You can basically by using a Go keyword with the function name, that function will become a Go routine. Okay, and also make sure, and we will discuss it again, that entry point routine, a main itself, is a Go routine. Even if you don't use a Go keyword, at least you will have in your application, at least you will have a one Go routine because of the main entry point function. So let's go over these bullets here and try to understand more in detail. So any function or method in Go language can be created as a Go routine. Okay, so it's pretty simple. You just write, a function or a method the regular way that you have been writing, and you can make them a Go routine just by calling with when you call it, just use a Go keyword in front of it. So a Go routine is nothing but a lightweight thread managed by the Go runtime system. Okay, so it's a very lightweight. It's comparing to the OS thread, and that's why it is able to run thousands of Go routine without any issues because the stack size is much smaller. So Go routine exists only in the virtual space, okay, of Go runtime, and not in the OS. So basically, since the Go routines are not the OS threads, they are not the part of OS thread. Okay, so they are basically within the runtime of the uh, Go application. Okay, there's the runtime system when you create your own Go application. So Go routine exists only in the virtual space. That's the key part to remember. So Go runtime scheduler manages Goroutine's life cycle. Okay, so it's a responsibility of the runtime system that is provided within your Go application. Uh, the memory consumption of Goroutine is about 2 kilobyte, like we just talked about it. Okay, and um, that's why you can run thousands of Goroutine in comparing to the OS thread, which requires about 1 megabyte or even 2 megabytes, in between 1 megabyte or 2 megabyte of stack space. Okay, so as you can see, 2 kilobytes comparing to 1 megabyte or 2 megabyte of stack space. So it's much more, OS threads are much more heavier. Okay, so the stack size of Goroutines can grow or shrink according to the need by an application. Okay, so the stack size could go, it's not always like a 2 kilobytes. It could go bigger based on how the Goroutine is written, and also based on how your Goroutine is running, and it has to have some memory allocated, and the variables, how they are declared within the Goroutine and so forth. So that's why it could go grow or shrink based on how the Goroutine is written. Only one OS thread might be supporting thousands of Goroutine. So as you can see, just one thread, one OS thread would be supporting the thousands of Goroutines. Okay, so that's why it has M to N mapping. So M meaning the OS thread, N meaning that Goroutines. So there could be a one OS thread with 100 Goroutine. Okay, so that's how the Goroutines basically utilizes the underlying operating systems, uh, code, or underlying or utilizes the CPU once it get a chance, because they are mapped that way. Uh, so Go runtime maintains three structs. So this is what we're talking about is how the runtime Go runtime system, which is the part of every application, Go application that you write, how what is the architecture of the runtime system. So it has basically three struct for scheduling purpose. So it can schedule the Goroutines, because as you know, um, you know, even though they are Goroutines, and even though they don't, directly go into the kernel space and start utilizing the CPU, still, they are going to go based on how the Go scheduler schedules them. So within the runtime there is a scheduler. So within the Go language, once you write the Go application, within that application there is a scheduler, because that's a part of the runtime system. And that you know and to maintain all that, this runtime system is designed using these three different structs. So they call this struct one a G struct, which basically represents the Go routine. Okay, so represents a single Go routine with its properties such as stack pointer, base of a stack, its ID, its cache, and its status. So this struct is the one, G struct is the one which has all this information, okay, about the Go routine. Okay. And M struct, M is for stand for a machine. That's what the M means, machine, and that which represents the OS thread. So that means M struct keeps information related to the OS thread. Okay. Now remember, these structs are part of the runtime, Go runtime. Okay, not the part of the kernel. So when we say Go runtime, that means this runtime is within your application. Okay, so this M struct is within the Go runtime, and it keeps the information about the OS thread. Okay. It also contains a pointer to a global queue of a runnable routines. So it actually, runtime has two different queues. One is a global queue, and then the other one is a local queue. So in this case, mstruct also keeps contains a pointer to the global queue of a runtime, a runnable Go routine. So runnable Go routines, that means when their turn comes, they still have to go and utilize the CPU through the runtime system. Okay, so because runtime system is the one which is designed to support M to N, M meaning the OS threads, and N meaning, so we just covered that uh, M to N. Okay, so M meaning the OS threads, N meaning the your um, these Goroutines. Okay, so it has to support all that. So the current running Goroutine, will have to utilize the the OS thread to go and use the CPU when it turns comes. Okay, so it has to wait for its turn. So in this picture right here, what we see is this triangle represents OS thread. Okay, so that means this M means machine, meaning that this OS thread is going to be running on the CPU. This uh, G means right here in the circle means the go routine. Okay, and this rectangle, which P means it represents the process. Okay, so what we are seeing in here, we have two OS threads. This is one OS thread, and this is another one. Okay, so in this OS thread, basically, as you can see, there are these are the go routines waiting in the queue to waiting for their turn to come to utilize the OS thread. Because these go routines will be maintained by the runtime system. Runtime system, as we talked, it has its own scheduler. So when their turn comes, it will go and utilize the OS thread by going through this triangle. Okay, and then once it goes there, then it will, of course, will be using the CPU. So this is the very, like, at the very low level. This is how the go routines are designed to run. Uh, in here, we see the two threads, M, which each holds a context P. So we have two threads right here, as we just talked about, each running a go routine. Okay, so these are running the go routines. In order to run go routine, a thread must hold a context. Okay, so this is the context right here, so otherwise it cannot run. So context is set to the value of the function. So this go max, now you can set this in your application. How many, basically, how many OS threads that you want to keep it for the runtime system. So once you set this up in your application, that many OS threads you will have. So, but also remember, it's that doesn't mean that if you have only, let's say you have a 4 core CPU, and you set this to 6, that doesn't mean anything. That doesn't mean that you will get 6 thread for where you have only 4 core available. So you should not go more than what you have physically in your hardware. Okay, so meaning more core than what is in your hardware. So, but you have a way to set your application how many OS threads that your application should be using by setting this go max procs. Okay, this is how you can set your application to be able to utilize the your OS threads. Now let's actually look at, in the next slide, how this runtime system is designed. So this is a very high level, and hopefully this will give you little better view of how each application, what when you create your own Go application, what is within the application. Of course, you write your own code, but then once it compiles, this your compiler will put in this runtime in there, within your application. So the Go runtime starts a number of Go routine, which are, this is a garbage collector, scheduler, and user code. So, these all are started as a Go routines. Okay. Now, uh, as you see, this this is the whole is your application. Okay, and in within your application you have this runtime system which is responsible for talking or exchanging the information with the OS or kernel. Okay, and the runtime system is also responsible for basically giving out the memory to your Go program, and if there is a channel need to be created, and how many Go routines are going to be there. So your runtime system, which is the part of your application, is responsible for doing that. So because of this runtime system, it is like a way that your Go program is connected with the OS kernel. So this is like a middle layer. So OS thread is created to handle these Go routines. So your in the kernel space, the OS thread is the one which will be created, you know, to support the Go routines. So one OS thread can support hundreds of Go routines. Okay, so you use this max proc just now that we talked about very well, which limits the number of operating system threads that can execute user level Go code. Okay, so basically, you can decide all that within your application and set this Go max proc. So GoMax procs sets the maximum number of CPU that can be executing simultaneously and returns the previous settings. So either you can find out what the previous setting is by using this function, or you can set how many OS threads that you want to use within your application. So the Go program run with Go Max Proc set to number of cores available. Uh, so it automatically initially it's set for how many cores that you have it available in your hardware or in your system. So in the prior releases, it was always default to one. Okay, so in the older release of the Go compiler, it was always set to one. You cannot have more than one kernel thread, to support multiple Go routines. But now, the newer versions of the Go compiler, it allows you to set, you know, to your preference for utilizing the kernel threads for your application. So you only need to explicitly set if you are not okay with this newer Go version. So basically, the newer Go version will set to the number of available cores that you have. If you're not satisfied with this, then you can, if you're not okay with that, then you can use this to change the how many OS thread should be given to your Go application. So specifying a Go max proc value that is bigger than the number of available cores will not make your application run faster. Okay, and that's what I mentioned earlier. So don't think that giving a bigger number for this to get the more OS threads, it won't make your Go application run faster. So the OS thread can be most equals to however many um, uh, cores are available. So that is a key part to remember. It's no point of going over the actual number of cores available in your hardware. Okay, so basic idea is to um, uh, you know uh, utilize whatever the cores that you have it available. So now let's look at how the running standalone Go application works. So by default, every Go language standalone application creates a one Go routine that we just talked about. So your entry point main that we always have used for writing the Go application, your entry point main is actually is the first Go routine. Okay, so that's what we are looking at it. So this is a application, so we have a package main. Okay, and then we are importing the fmt package so we can utilize the print line function, and at line number 5 we are creating the function called show message. Okay, in that case this is just a function. So within the body of the function there is only one line, which is print line. And then we have an entry point routine right here at line number 9. Within the entry point routine I have a print line to show that we just started the main, and then call the function. So as soon as this we started this entry point routine, the Go routine is started, because entry point routine itself is nothing but a Go routine. Okay, and then it will just print out. It calls this function, and then once whatever is inside the function it gets printed, and then last line in the entry point routine gets printed. So basically the output is just like a sequential output. First line, and then the call to the function, and then the last line from the entry point routine. Okay, so that's the simplest Go routine that is used in the application. So now let's actually understand the calling the Go routine with the independently by using the Go keyword. Okay, so uh, so we have execute independent Go routines. So how do you execute? You basically make a call to them. So in this case we have a Go language standalone application, and you can run with many Go routine. Okay, and you can use, of course, the Go keyword. So when Go keyword is used, Go routine always run in the background. Okay, so that's the key part to remember. So even though you have a function just like a regular function that you have used previously, but as soon as you use it with the go keyword, that means that function would be running in the background. So the go routine do not synchronize. That's the by itself, without using any other syntax of the language. The go routine by itself, it cannot synchronize. Okay, so for synchronization we have another syntax that we have to incorporate, and we will go over all those pretty soon. So uh, when they are executed currently, so they do not synchronize when they are executed concurrently. So the main application will terminate before goroutine finishes unless blocking mechanism is used, such as, so blocking meaning that you want to make sure that your main entry point function doesn't terminate. And you put some sort of a block in there, maybe use a sleep or something like that, so the go routines will get the chance, because the once you start the go routine in the background, they could take a little longer time, but before even they finish, the main application finishes, main go routine that is within your entry point routine, it would finish. Okay, so that's why you have to use a blocking. So how you can use a blocking? You can use time package. Okay, has a sleep function, so you can use that for blocking. Okay, that's the only thing it will do. It will just for certain for a 1 second or 2 second, whatever the time that you decide, it will be blocked. Okay, meaning your application would not terminate, and in the meantime, go routine will get a chance to finish whatever it was supposed to be doing. Okay, so that's the reason that you would want to do the blocking. So basically, you can also use the sync package, which has a wait group in there. Okay, to do the synchronization. So that is also can be used for blocking as well. You can use the from the sync package, there is a mutex. Okay, you can use the mutex logs as well for blocking. The best one to use is the channels. So used for communication, to share the data, and to synchronize. Okay, so if you have if you use the channels, you can use the channel for blocking, as well as basically transferring the data by using the channel. So it provides a multiple purpose. So a process is blocked. Okay, when we talk about the blocking, what does that mean? So a process is blocked when it is waiting for some event, okay, such as resource becoming available or the completion of IO operation. Okay, so that's the reason that it is blocked. Okay, so that's what the blocking means. So it is, if a process is not blocked, okay, then go routine will not get a chance to execute, because as we just talked about, that the go routine is running in the background. Okay, and it would not, even though it is running in the background, but the main application or the main entry point go routine the main entry point function that also has a go routine, it will terminate. So then basically your program is stopped, and the memory that was allocated for that program will be cleaned up by the garbage collector, and your go routine which was running on in the background will be removed by the garbage collector basically. And but it would not be able to finish, the go routine will not be able to finish whatever it's supposed to do because of the termination of the main go routine. Okay, so let's look at this example, EX 7-2. Okay, and in this example, what we have is, we have a application. So that means we will be creating the executable. So we have a package main, and then in in here we have a one function, show message. Okay, just like in the previous example. But in this example what we have is that within the main or within the entry point function, we are calling this show message by using a go keyword. Okay, so that means we are making sure that show message is going to run in the background, and it is going to be running as a go routine. Okay, so that's what it is called, the go routine. Now, as you can see, it starts at line number 12, it starts to run. Okay, but the problem is that within this main go routine, there are two messages, and there is no blocking. There is nothing is done to stop this main entry point to get a chance to give a chance to the show message to run. So it will start the because of this go keyword, the show message will start running in the background, but right away this main entry point will finish before this show message will get a chance to display this message. Okay, so that's why you see only the output with this two lines: started, main started, and main stop, and that's it. So to make sure that this application get a chance, we need to have a concept of a go routine, and we will cover that in unit 2, chapter 7. So let's move on.